Welcome to today's masterclass. I'm really glad you're here for this explainer because today we're rolling up our sleeves to demystify one of the absolute most common mix-ups in all of science. We throw these two words around every single day, right? Usually using them completely interchangeably. But in the world of physics, they are entirely different beasts, total game changers. I'm talking, of course, about mass versus weight. So let's dive right in and clear up this confusion once and for all.
On our syllabus today, we're focusing on two core learning objectives. First, the definition and units of mass. And second, force and gravity's role in weight, which actually includes a really handy quick calculation trick.
All right, part one, defining mass and its units. Let's get to it.
So, simply put, mass is a measurement of the amount of matter present in a body. Now, I know the word matter can sound a little, abstract, but honestly, just think of it as the physical stuff that makes up an object. Every single atom, every little molecule, it all counts towards the mass. It's basically a physical tally of how much actual substance is sitting right there in front of you. And honestly, this straightforward comparison really hits the nail on the head. Imagine a cup holding 2 kilograms of sugar, and another cup holding 4 kilograms of sugar. What is the actual, literal physical difference there? Well, the 4-kilogram cup physically contains a greater amount of matter. It occupies more space with sugar particles. It literally just has more stuff crammed inside it. Let's reinforce this with something we do all the time. Imagine you're at the market shopping for dinner. You see 1 kilogram of vegetables priced at $50 and 2 kilograms of vegetables priced at $100. Why are you paying double for the 2 kilograms? Well, because the mass is exactly double. You're quite literally paying for double the amount of physical matter. The price scales perfectly with the physical amount of stuff you're lugging home. Okay, let's run through these foundational rules of mass. First, the standard SI unit for mass is the kilogram. Simple enough. When we want to measure it accurately, we use an electronic balance. Now here's an absolutely crucial physics term. Mass is a scalar quantity. What does that mean? It means it only has a magnitude, or a size, no direction whatsoever. You can't have a downward mass or a leftward mass. It's just an amount. And finally, mass is constant everywhere. To perfectly illustrate that constant everywhere rule, let's look at Tom. If Tom has a mass of 60 kilograms here on Earth, his mass is exactly 60 kilograms. Now imagine we strap Tom into a spaceship and shoot him all the way to the moon. When he steps out onto that lunar surface, his mass, it remains exactly 60 kilograms. The amount of matter making up Tom hasn't changed just because he changed his cosmic zip code. Which brings us to part two, force and gravity's role in weight. Now, before we explicitly define it, I want you to consider a seemingly simple question. Why do objects fall toward the Earth? Seriously, if you drop a pen right now, why does it plunge down instead of, say, floating up toward the ceiling or just hovering in midair? It's a fundamental question humans have literally asked for centuries. The answer, as you've probably guessed, is gravity. But this brings us perfectly to our new definition. Weight is the downward force of the Earth due to which objects fall toward the Earth. Okay, the absolutely crucial point here is that weight is not an amount of stuff like mass is. Weight is an actual physical downward pull. It's a force created by the invisible gravitational attraction between an object and the Earth.
So here's a specific physics question directly from our source material that often trips people up. Why do heavy objects fall faster than light objects toward the Earth? To really wrap our heads around the answer to this, we need to transition into the underlying math that makes it all happen.
Let's walk step by step through this beautiful little piece of physics. Step 1, we start with Newton's famous second law of motion. Force equals mass times acceleration. F equals ma. Step 2, since we're talking about objects falling, the acceleration they experience is entirely due to Earth's gravity. So we just swap out that acceleration a for Earth's gravity g. And finally, step 3, we swap out the general force F for our specific downward force, weight, W. And look at that resulting formula. W equals mg. Weight equals mass times gravity. It's like a giant puzzle coming perfectly together. And this brilliantly illustrates our answer regarding falling objects. Let's say W1 is the weight of our heavy object and W2 is our light object. Since gravity, g, is a constant for both objects as they fall, these equations mathematically prove that the downward force, the weight, directly depends on the object's mass. The heavy object has a larger mass, so it experiences a significantly larger downward force pulling on it. And according to our source material, it's this greater force that causes it to fall faster.
So let's quickly summarize the rules for weight to contrast with our mass rules.
Because weight is a force, its standard SI unit is newtons, denoted by a capital N. It is not kilograms. And unlike mass, weight is a vector quantity. This means it always has a specific direction. In our case, because it's gravity doing the pulling, that direction is always aggressively pulling downward toward the center of the Earth.
All right, moving on to part 3, the quick calculation trick. Continuing our focus on gravity's role in weight, remember our formula? W equals mg? Well, Earth's gravitational acceleration, g, is technically about 9.8 meters per second squared. But, for a quick calculation trick and everyday math, we can smoothly round that up to an even 10 meters per second squared. And using 10 as our multiplier makes things beautifully, brilliantly simple.
You can see just how foolproof this trick is. To find the weight in newtons, you literally just add a 0 to the mass. That's the whole shebang. If your mass is 20 kilograms, multiply by 10 by adding a 0, and boom, your downward force, your weight, is 200 newtons. An 18-kilogram mass, that's a 180 newton weight. A massive 286 kilogram object, just pop a 0 on the end, and you get a weight of 2,860 newtons. It works flawlessly every single time.
Now let's set up our final takeaway. We've established that weight is entirely dependent on gravity, right? Well, if we compare the Earth to the Moon, the Earth is huge and has a massive amount of gravity, exerting a really strong downward force. The Moon, however, is much smaller, so its attractive pull creates a significantly smaller downward force. Which brings us to this final provocative thought experiment to perfectly wrap up today's masterclass. If Tom's mass is always exactly 60 kilograms because the physical amount of matter inside him never ever changes, but the Moon pulls on him with much less force than the Earth does, what exactly happens to his weight when he steps out of that spacecraft? I'll let you chew on the math for that one. It perfectly synthesizes everything we've learned today about mass, gravity, and force. I hope this explainer leaves you eager to explore even more physics. Keep questioning the world around you, and I'll catch you next time.